And today, that's why I'm saying we are moving now to the first vibration. And as you can see, we move to the next slide. Now we are introducing back another part, because our equation of motion, as usual, if you remember, you say the m times acceleration, we are moving plus damping times velocity. Remember, we are talking of, for it to be like this, we are talking of viscous damping, plus stiffness times displacement is equals to this is good morning and welcome to our class today. Today, I believe we are on our fourth class in Introduction to Structural Dynamics. Thank you for all those who have joined us today. And just make sure you drop your registration number. Registration number is enough. Don't leave your name. I think I have your names already. But that's no harm. If you want to write your name, registration number is okay. Good. Just a recap of what we've been doing is that we've been concentrating on single degrees of freedom systems. And we said is where that we just need one coordinate to describe our motion, right? Either one x direction that's enough to describe our vibration or oscillatory motion. Allow me to just stop this video so that I don't hide anything. So what we are saying is this. So we're saying we've been looking at free vibration, where we have talked about undamped and damped cases. Today, now we move to the second part of the single degree of freedom case, where we are looking at the forced vibration. Remember, if you recall well, we have the fundamental equation of motion. And what we are just doing is that we are starting with the simplified, we are removing a number of unknowns that equation so that we can be able to develop concepts easily. And then we continue now bringing them back as we try to simulate or emulate the actual scenario or the actual real life cases. So because we say, like, when you say free vibration, which is undamped, that's kind of an ideal world. Yeah, there will always be damping in real life cases in structures. And of course, for free vibration, the motion might be interesting when you are developing the basic concepts of structural dynamics, but you realize the motion will not continue for a long period of time, okay? So, and most of the vibration that you're going to, or we consider in real life, there is always kind of a force that have initiated those motions, all right? I mean, the vibration which are of interest. Remember, we said like the free vibration is like the case of a pendulum, where you cause the initial displacement, then you release. But when you come to structures, you're looking at the issue of like earthquake or impact loading. So there is kind of an external force that will initiate our motion, our motion. And those are the kind of analysis that are interesting to us in structural engineering, all right? And today, that's why we're saying we are moving now to the forced vibration. And as you can see, we move to the next slide. Now we are introducing back another part, because our equation of motion, as usual, if you remember, we say the m times acceleration plus damping times velocity. Remember, we are talking of, for it to be like this, we are talking of viscous damping plus stiffness times displacement is equals to Ft. This is the fundamental equation of motion. We say, whether be it single degree of freedom, multiple degrees of freedom, continuous system, this is the fundamental equation of motion. And as you can see, we are assuming zero on this side for free vibration. And now we are playing when there is no damping, we remove this component. And when there is damping, we introduce it back. Now we are saying we want now to reintroduce this part back for the force function, such that this is our system. We have the damping component, and this is represented like this kind of a standardized table where we show the dashboard. We call it dashboard. Yeah, dashboard that represents damping, right? And so we have the damping is represented by C, the stiffness. Remember the stiffness. All these are kind of forces, or they are kind of the component. This component. They kind of are trying to restore our motion, our structure to its initial resting position. Okay, so they act in the opposite direction to the externally applied force. Now we are saying the applied force now is no longer equal to 0 because we are in forced vibration. And this is the direction of our motion, positive direction. So going backward will be negative. Then because of the mass m, remember we talked of the Albert's principle. The Albert's principle states that a system may be set in a state of dynamic equilibrium. That is, if you want to set a system in a state of dynamic equilibrium, you can add an external force, a fictitious force that is commonly known as an inertial force. So I find the Albert's principle, the statement, to be kind of restating what you already studied in the Newton's law of motion, the second one, F is equals to ma. Because whatever he's saying is that to set this system in a state of dynamic equilibrium, so we are saying now to ensure equilibrium, you apply a kind of a fictitious external force, which will act, of course, because of this mass and this direction, we are going to have inertial force, F is equals to m. Okay, we always know this equation. So the inertial force that we apply acts backward. And if you can try to imagine this, remember when you come to, let's say you are in motion in a vehicle, and then that vehicle comes to a rest, you kind of try to continue in the direction that the motion was occurring. Or let's start when you are at rest. When you are at rest and the vehicle just jumps forward, what happens is that you kind of there is a force that tries to push you backward in the opposite direction of the direction of our motion. And that's why now the Albert is stated that Newton's second law, he said that to set your system, and this could be important, maybe you could note it somewhere, because it's a statement of the Albert's principle. But you have your note, I don't know whether I had made that statement before in lecture 2, that to set a system may be set in a state of dynamic equilibrium by adding to the external force a fictitious force, fictional, not real, fictitious. Yes? Fictitious force, which is commonly known as the inertial force. Now, this forcing function, the force now here will come into different natures. And remember, we talked of the different types of loadings that we can experience in lesson 1. We talked of, we can have periodic force. I feel forced to subscribe and comment. You should have subscribed a long time ago. Levi. Okay. So we are saying the forcing function, the harmonic forcing function, not harmonic. I'm just taking you back to lesson number 1, where we talked of the different types of the loads, dynamic loads, because this is what we are talking of this year. This is now our point of interest, the forcing function, or whatever you are calling that, the external force, for it to be a force vibration. Now, this force we talked of deterministic or stochastic. Deterministic are those that can be, they can be expressed as a function of time, like you can be able to predetermine using probability. But stochastic are random. And we give an example of an earthquake loading. The earthquake loading, of course, we have data collected over time, but it's just prediction. It's kind of, you cannot use a mathematical equation to accurately represent the load that will be experienced at a certain in the future. But in case of the deterministic function, deterministic load, the one that can be determined, you can approximate them using a mathematical function. We talked of different types. Some of them are periodic, others are non-periodic, and we say periodic are those that occur repetitively. And in a periodic, we had a case of harmonic. Harmonic is now when that repetitive motion occurs in form of sinusoidal wave. And I was giving some example whereby I was saying, if a machine resting, let's say this is a slab, and for you real life cases, I was considering a case whereby you may have in a workshop, and there is a machine, because there are many machines there, let's say like a red machine. And inside it, of course, there are components which are moving up and down, they are rotating. And maybe because of the way it's supported on the ground, its position on the ground, there is some unevenness that causes some vibratory effect to be felt on this slab. Remember, if it was perfectly laid on this slab or on a beam, maybe there will not be any up or down motion. But if because of the unevenness, because of the vibration or the motion that is occurring inside the components of the machine inside, maybe you may feel like there is up and down motion. And we say because it's repetitive, and this machine, of course, it occurs under after a regular time interval, that motion might be described as a function of sine or cos wave, what we call the sinusoidal function. This is from your physics. And we talked of deterministic loads again, which necessarily don't have to be, they do not have necessarily to be harmonic, but they can be expressed as a function of time. So they are deterministic, but they are not harmonic. And for example, you're looking at different cases we are giving here, step loading. You see, like this load, the first case, the load P naught does not change, vary with time, but it's applied up to a certain time, right? Now, the ramp step loading is like the load first increases, then remains constant. General loading cases is whereby now we are just assuming this function could be, but it cannot be, it's not a sinusoidal function, but it's, the curve is just random, okay? So what we are saying is that these cases, they can be expressed as a function of time. You see ft. So like the first one we are saying ft is equal to p naught, that's the constant. The second case we are saying up to the time t is equal to t naught, is a triangular. You know, it's like it's increasing. Like we can use the gradient to be able to approximate at any time where t is less than t naught, we can be able to use the first equation to be able to obtain what is the force, right? And after that, of course, now after time t is equals to p naught, our load or forcing load becomes a constant p naught. Okay. The general case loading that we are talking here is now like when you have a curve, but it's not a sinusoidal. Remember the case when we are using the trapezoidal rule of Simpson's rule to calculate the area. That's when we had a general kind of a general kind of curve, right? That might not be expressed analytically or using an analytical function, but still is a function of time. Okay. Now, for us to be able to study force vibration, we are limiting ourselves to those pulsing functions that can be expressed as a function of time. That's why we are not going to non-deterministic or stochastic loading. Okay, that one we are going to look at it towards the end when we look at the introduction to earthquake engineering. So stay tuned together with us for more learning on the same. Now, of course, as you know, and as is my trade, of course, in many books, we always start with this basic principle, the easier one, so that you build your concept, you understand the concept, then you can move ahead to now the more complicated case. So what does this mean? The sinusoidal function, the harmonic excitation of harmonic loading, we can be able to express as a function, as a sine function or sinusoidal wave. So this is easier because we can go ahead and be able to solve this kind of, the solution of these trigonometric expressions. When the differentiation, remember our calculation or our course here, we are dealing with the differentiation so much. We are dealing with ODE, ordinary differential equations, right? So that's why now when we look at this kind of function, we see, this is easy, we can be able to differentiate quite easily. And that's why we start with harmonic loading or harmonic excitation. And further, we simplify. We first say, let's assume there is no damping, okay? So our case now becomes further simplified because our equation is like this. Remember, mu, we could have, if there was damping, we could have had C, B, okay? But this time we are saying no damping, so that component collapses. And as you can see now, our dynamic system representation is like this. This is a dynamic representation. Remember, dynamic system from simplification from the real scenario. Remember, this system could be, we have simplified from a structure like a photo frame. Yeah. And then we have expressed this as using dynamic representation so that you can go now to the mathematical model. And this was explained in lesson 1. You can look at it again. How we move from a complex but the reality. We simplify first with the physical system. Then we move to the dynamic system so that we can develop mathematical model, right? So in this case, you can see there is no C here, so the dashboard is missing. And our equation is as simple as you can see in equation 45. This is what I was calling the Albert principle. This is the Albert force, the fictitious force that is known as the inertial force. You can see it's acting in the opposite direction to the direction of the forcing function. Why we are using the forcing function instead of just saying the forcing load is because it's varying with time. It's a function, all right? You can see at a different time in that, of course, when t varies, of course, the load experienced on this body will vary, right? So our fundamental equation, and as you can see, if in this equation, if it was free vibration and damped, this part would have been 0. And this is what we started with. And they said this is second order linear homogeneous ordinary differential equation, right? And when this now is no longer 0 because of the harmonic excitation or the forcing, external forcing function, then our equation is no longer harmonic, it's no longer homogeneous. Our ODE is no longer homogeneous. Now, if you look at this equation, there are two frequencies. Okay? Okay, at this stage, why we have used this is because the externally applied force. Remember when we had the free vibration, this part was 0, but our motion, we are analyzing our response, which was our displacement. We express it as of course, we found it's going to vary as a wave. And for free vibration. And that wave, of course, there is the frequency. That frequency is the frequency of the system, of our. Now we have the frequency of the applied load, external force. And this one now, of course, when we do our analysis, we're going to have the two frequencies. The other one, of course, is not explicit here because we have not solved here. But this one is just direct like this, right? And we use, to differentiate the two, we are using capital omega. Remember the other one is small letter omega, its capital letter is like this. And to differentiate the two, when I'm speaking, I'll be talking of omega to represent the small omega, and then I'll be talking of ohm, right? Because I know in physics you talked about the ohms, the ohm, the unit, right? So this equation 45 has got two parts. Now you know you have refreshed your ODE. You have the complementary solution. The complementary will be when our equation is homogeneous. If we assume this component to be equal to 0, yeah, then we are going to get the complementary solution, which we obtained, of course, for free and damped vibration. So this is the repetition of equation number 8. Again, when this forcing function is not equal to 0, then we are going to get what we call the particular solution. Okay, the particular solution, UP here. You're going to get this. This is when now the equation 45, the forcing function is not equal to 0. Okay, now let's now we are saying the capital U here. Don't confuse the capital U here with the small u. The small u is our response, our displacement, but the capital U is the amplitude of the forcing function. Remember, we have assumed that the applied external load, the forcing load or the forcing function, is a wave or can be expressed as a sinusoidal function because we assumed a harmonic loading. So that externally applied load force, if it's the vibration inside, maybe a piston inside a machine resting on a beam in a structure in a good, we are assuming that the up and down motion, we can be able to get the amplitude of that external applied force. So we can be able to get the amplitude of the external force. At the same time, our structure, because it's vibrating, there shall be the amplitude or the displacement, the small up. Okay. Now let's get the solution. Of course, with the first part, we knew, of course, when for the complementary solution, when the forcing function is equal to 0, of course, we know how we obtain for free vibration this equation, and of course, we were able to determine what are the coefficients A and B using the initial condition. Remember, we said we are solving an initial value problem. Now, to substitute, now this is a solution, typical solution, the particular solution UP, the equation 46. So you're saying substitute equation 46 into 45, and of course you cancel common factors. To do so, of course, remember we are substituting this equation 45, the second derivative of U So you are going to differentiate equation 46 UP twice, and then you substitute in equation 45. And of course, the common factors are this sine omega t or sine ohm t, so that you are left with this equation 48. And now this is just a matter of rearranging. Now we end up having the amplitude of the forcing function can be expressed as f naught of a k. So remember here, what we just happened in equation 49 is just dividing through by k, and then using what is known already. We defined what is frequency ratio, r, which was equals to ohm of omega. And so our expression can be simplified, or amplitude of the forcing function can be simplified in equation 49. And therefore, our complete solution to equation 49 will have two components. Of course, this is the Ari statement. This is Ari statement, equation 49. That the wording that we had put, that we have two parts, 1 and 2, complementary and particular solution. So the complementary, the one I have highlighted in red. Now the omega, you can see it's the small letter omega, and then the particular solution. Now we have the frequency of the forcing function. So if you look carefully here, the second part, the particular solution part, is the one that contains the aspect of the forcing function. But the complementary solution, this is kind of a free vibration motion. And you're going to see what does this mean for our equation. But this now is our response. This is our complete solution. And what remains to be done or to be obtained is just what are these A and B. But remember A and B, we had calculated for the complementary solution, for the free vibration in the second lecture. So let's see now how to obtain here in this case. I have just realized that equation 51 is just a restatement of the equation 50. Yeah? So it's the same thing. Yeah? I was trying to bring it to this slide. So you can delete that. Yeah? But I said I'm not going to change this numbering because I have to change all the way and keep the end of the lecture. So for us to obtain the constant A and B, we are saying you assume the initial condition. Remember, A and B in equation 50, or if I stick to equation 51, A and B, we cannot just take them directly to be the constants or the coefficients that were calculated for free vibration. Remember, there was a case, is it the last lecture, lecture number 3, that I talked of redefining the constants or the coefficients, because A could be 5, but I use it again in another equation. A could be 10, right? Why it's different? Because now we have this component here. So that's why we have now to recalculate again to be able to obtain using the initial condition. You're saying assuming at time t is equal to 0, u naught is equal to 0 and v naught is 0. This is an assumption, so that now you can use this known initial condition, initial values. You substitute in equation 51, you'll be able to obtain what is A and what is B. And that should be as easy as ABC, as these letters. So once you obtain what is A is 0, and then B is this part. You substitute, of course, our equation 51 becomes, as you can see, in 52. And again, here we have just jump some steps, because if you remember, there is the identities that we are utilizing to simplify our motion, where we say the issue of sine A plus B, right? We said sine A, cos B, sine B, cos A, like that. And this one is what we have done in this case. Because you have seen we have sine omega t and sine ohm t. We expand, and then we express it in a compact form as this. So there is a step that you need to do after obtaining the A naught and B naught. You substitute them here, this collapses there. And then we are rewriting these two different components in this value. Okay. So that's why I said it's good to do the practice in this, so that you don't just look at the equation and they seem so easy. But later on, when you try to work them out, because you've not done enough practice, you find like you are stuck somewhere. Here, I've just done the step because I know in the previous lecture we are doing step by step. But at this time, I know you already know that we are using those identities. All right. Now, if you look at this, this is the ohm, where we say this is the frequency of the forcing function, and this is omega. This is the frequency of for the free vibration. So for the free vibration, it means This part is only for a certain time, and then it dies out due to damping, right? So we are calling this as transient response. Transient is like for just some time, like the way we are here. We are transient in this life. It's just for a short time, and then we just go. But this second part, this part where we have the omega, because there is, as long as the forcing load is not eliminated, it's not removed, it will continue causing the motion. And this is the part that will persist. This is the motion that will persist. And this is what we call as the steady state response. So that's what is. You may wonder why this term. The steady state response. This ensures that our motion continues. Transient response, meaning it will vanish due to damping because there is no forcing or external force that is applied to aid our motion. And just this one restatement, we are going to see how this occurs. We are saying when the forcing function, when the frequency of the forcing function equates the frequency of our structure. Remember, the omega is the frequency, the small capital omega is the frequency of our structure. When the two rhymes, we talk of they are equal, we talk of resonance occurring. And therefore, the amplitude of our forcing function becomes infinite. Okay, so you can see here. Because R is equal to a 1 over omega, and when these two are the same, 1 over 1 becomes 1. Here, 1 minus 1, the denominator becomes 0. So of course, when you divide by 0, it becomes infinite. So that's when we talk of resonance occurring. And I know in waves, in introduction to physics, I believe in first year's courses, we talked of destructive interference and constructive interference. Okay, this is when now sometimes the resonance could occur and so on. Good. Let's see, but we are going to see later on graphically what this means. Now we have already kind of developed some basic concept on forcing function, forcing vibration or forced vibration, and we have seen the two components, the steady state response and the transient response. Transient is like we studied it already in the previous free vibration. So we might find that our point of interest would be the steady state response. Now let's see to the second part. We had assumed no damping, but now let us reintroduce the damping part. Let us reintroduce this part C, right? So our body, this is free body. You should practice. As an engineer, it's always good to communicate using, we have a common language of sketches of drawing. You can communicate to somebody when he doesn't understand your language. So this is a free body diagram. It's always good to practice once you visualize your body to break it down to see the free body diagram so that you can understand what those forces are acting on that particular body. Okay. So you see what we have reintroduced now is this, the damping component, CV. So our equation 45, now we reintroduce this damping component. We have the equation 53. Again, we are saying the solution or equation 53 has got two parts, of course, the complementary and the particular. And the complementary is obvious because if you remember the complementary, we are assuming this is equals to 0. So this equation just becomes free vibration of damped single degree of freedom case. And we had covered that in lesson number, I believe, number 3. And as you can see, this is a restatement of equation 36 in your classroom, right? We found it to be in this form. Now, the particular solution, of course, will have two parts, C1 sine omega t plus C2 cos omega t. So now here, we're saying you substitute equation 54 and 55 into 53. Now here you have a lot of work. To substitute, of course, equation like this equation 54 into this equation 53, you need to do the differentiation. Once and twice so that you can get what is velocity and what is the acceleration. Then you substitute and you simplify. And you equate the coefficient of sine and cosine function so that you are going to obtain the constant C1 and C2. You could also say A and B, but to avoid the contradiction, you're just using different notation, C1 and C2. So you need to work that out so that you obtain what you are saying. C1 and C2 is given in this expression. All right. The book that I gave, I hope that the class lab shared with you. There is a book, a very good book that I shared with you, which is our main reference. I believe there is a working out of this. Of course, even many textbooks, they just summarize, because I know that this one you covered in another course, that is in mathematics, in algebra, in calculus. So it's just a simplification of this on the same. Again, remember we introduced some identities which we used in lesson number 3 to simplify our expression, whereby we employed what we call the Euler's expression. The Euler's expression. Now, employing that, the Euler's expression helped us to do away with the imaginary numbers, the square root of -1, which is equal to I, by relating it now to the cos and the sine. So by employing the Euler's relation, our equation 53 can be written as shown in equation 57. Of course, you can see the forcing function. Now we have expressed it in terms of the imaginary number. And we are saying, this is a note, that only the imaginary part, the forcing component, F naught sine omega t, is active. Thus, the forcing function UP is the force is of the form CE is to power I on T. Okay, I want to again, of course, to digest there. And this now we are saying from equation 50, that we have a compact form of the particular solution. We substitute in equation 57, okay, in our equation 57, and you cancel the common factor, E raised to power I on T, you're going to have equation 59. So this is a matter of derivation and the calculation, hard calculations, so that you can see how you are obtaining the value C and the value UP. And this one, you can leave it for practice, so that as you work them out, step by step, you do not just show this final answer, but we need to see the workings, the derivatives, the derivation that are happening, the differentiation that is happening, even deriving the basic concept that might be necessary, so that you may end up having the part or the equation 60. Okay. I find Alano is asking, if I am building a structure where vibration is expected, like earthquake, how do I know if my structure will undergo damping or not? Is it like a machine that ensures a damping? Hmm? Well, how we are moving, we started with vibration, but I talked of free vibration being kind of, okay, no, you're not asking about the forcing function, you're asking about the damping. Damping is kind of inevitable. It's basically kind of will occur. But one thing that you'll find in analysis, this analysis part, then we come to the design. When you come to design, there is a code. The code which are factored in. Like, let's say you are doing a seismic analysis. In Kenya, we have the seismic zones. And in those zones, there are now the factors, because after a long time studies that have been done. So when you come to the analysis, when you are doing the design in itself, the aspects of damping will kind of be taken into consideration in the code because of the factors that we are going to use, the factors of design. Okay. Now, for you now, you're saying, let's say I give you a problem, like you are given a problem to solve. Most of the cases, you find like in a problem like one, you're going to see there are assumptions that are given. Okay. Now, when you become an engineer, there are responsibilities that rest upon you by the time you carry that title. Now, for you, when you are doing the analysis, there are assumptions that you make. But they are not just assumptions based on emotion. They are based on, one is the core, the existing studies, the geographical location that you are in. Like now, if you were given a structure to analyze a multi-story building in Nairobi, and then you assume there is no damping, then it becomes interesting. Why did you assume that? Because we are saying there are different, assume that you already know the different types of damping that will occur. There is damping even because the external damping, just because even of the fluid, the air, the structure is vibrating in an air, it's not in a vacuum. So the assumption you make is like, they are based on your understanding from the theoretical point of view, but again, you are not alone because you are guided by the code from the experience of other people, and which are brought together, constitute the design code. So I hope I'm trying to bring it out. I know you are wondering, like, now if I'm told to design, how do I know whether I consider damping or not? Of course, you design using code. But I'm telling you, it's like obvious. Even if there are no code, then you are told to analyze a structure. Design is when you use code. Analysis, you don't. Analysis is your theory and understanding. But of course, there is a literature. But if you assume there's no damping for real life structures, then we wonder, where is that structure vibrating in? What kind of a medium? Is it in a vacuum? We are talking even of the internal, and this is what we are concentrating on, the internal friction of the particles of the material that are being used, which is inherent characteristic and have kind of to be there. Okay. So there are assumptions you make, logical assumption, and there are others you make guided on the code. Good. Now we move ahead simplifying our equation. We are saying in polar coordinates. Polar coordinate, remember we talk of rectangular, like when you're in Cartesian coordinates, rectangular and polar coordinate. Polar coordinate is like you want to express the coordinate. Let's say this is your origin. You express that point. So it's kind of, you can express this direction using the length is r and the angle theta. At the same time, for rectangular coordinate, the Cartesian, we can express this part using the x and y coordinate. Okay, so we are saying, or the other here is trying to move from saying we can also express it in polar coordinate, that is using the angle, the angular, because our motion, of course, we start with angular motion. When the motion, even though you are talking of the motion going like that, it's kind of a circular motion, like that. That's why you find like the period we talk of the 2 pi, we go to 180, and of course, it's like we are completing a whole rotation, circular motion. Okay, so that's why now we are interested in talking of the polar coordinate, and we have introduced what is theta, this component in equation 62. So the response, we are saying the response to the force. This is the forcing function, remember? So the response, that is the imaginary component, the one that have got I. The response is shown in this UP, F naught sine all this that is under that, the square root of that equation 63, or in compact form, expressed in equation 64, where U, remember the capital U, we say this is the amplitude of the steady state motion. So all these component is what we are calling the U, the amplitude. So you can see it's the one that is written here in equation 65 as the amplitude of the steady state motion, the amplitude of the forcing function's motion. Because of the forcing function, the forcing load, there is a motion that ensues. The motion of that forcing function, not the motion of our structure. That's the amplitude D. Now, in terms of dimension plus quantity, it's always good. When you find us expressing in terms of ratios, it's because we want to deal with dimensionless quantities. We are saying equation 63, 62, 63, and 65 can be written as, so let's see, what is 62? 62 is this one where you have the angle theta. 63 is the response, and 65 is the amplitude of steady state motion. So we are using ratios. Remember the ratios you defined initially, okay? You remember this frequency ratio, R, don't confuse that with the xi, where we talked of the damping ratio, C of a CR. So this one simplifies the equation 63 by using those ratios. The equation, again, 67 simplified using the same. Allow me just to pick a code here. All right, sorry for that. There was a call that I could not have avoided, but I think it has also given you some breather so that you can look at this equation. I know there might be overwhelming. As I say, that sometimes the derivation themselves, they might be tasking, they're time consuming, but it's good. It's good so that you don't just look at the equation and then you say, I mean, you are not just copying things. You're engineers, in as much as you are not in pure mathematics, but it's good to understand this component. Okay, so good. So you have simplified, express it as a dimensionless quantities, ratios using the ratio that we defined before, damping ratio, frequency ratio, right? And it simplifies to as shown in 68. Therefore, the total response, remember our statement, the complementary solution and the particular solution can be rewritten now using our compact form as shown in equation 69. And now we define another ratio. We are calling it dynamic magnification factor. And this is the ratio of the steady state amplitude to static diffraction. Okay. And as you can see, the dynamic magnification factor, we are saying is the amplitude of the forcing function divided by the static diffraction. Remember, static diffraction is like when we say F is equals to K delta, the Hooke's law, that delta. Okay. And by so, now of course, using the ratio, our equation simplifies as shown here. So dynamic magnification factor can be expressed as shown. When resonance occurs, this is what I was defining on resonance. When resonance occurs, we have, of course, the dynamic magnification factor, of course, simplifying to this 1/2 xi, right? And here in this graph, we are showing for different values of magnification factor and frequency ratio, we are trying to show you how the amplitude will vary, okay? How you see how the D varies with the frequencies, okay? The frequency ratios are for different, so here we are combining three, or we are relating three components, the D, R, and the xi, okay? And of course, you can see at this point, when you're saying xi is so small here, when it's so small, it may end up here at the bottom, we have the lower component to be equal to 0. The dynamic magnification factor is too great. That's why now we talk of the resonance. It's too big. But for the resonance, our resonance to occur at this R is equals to 1. You see, 0.1 resonance occurring. It's like the amplitude is too great, almost infinite. Of course, this may lead to total collapse of our structure. Okay. All right. All right. So take your time and digest these. These expressions, these derivations. It's an interesting thing that although it might not be for examination purposes, maybe it might not be so much crucial, but for your understanding, it's important. But again, as I said, the derivation might be as you can look at them, but they can be as simple as you do your practice. But application of this equation is very, very easy. It's straightforward. And this is what now we want to do, or we want to check in this using one example. Okay. And somebody is asking, do you have to cram all these equations and formulas, or you provide them in the case of exam? If you noted that from like the last semester, for the equation that it was not necessary it was complicated to recall. Of course, we provide for that. Maybe for example purposes, you should be able to derive these. But for example purposes, maybe the direction that you'll be given be just a small one, right? Maybe not. But let's see. We look at we have solved now. This is our example 5 in this course. You'll see all the examples that you have looked at, even the examples in the books. The part that you need to recall, they are simple equations, right? They are simple equations, like remembering what the ratios, remembering what is why we are using these ratios. You see, dimensional ratios and all that is so that we can simplify our equation to a level whereby they are easier to recall. Okay, but for sure, I never advise for cramming, but recalling. Because now cramming again, it's not bad. The ideas you need to remember, but that's not the point of testing that. Yeah. So let's see with the examples, and then you see how you don't even need to go back and look at those equations. You are given a single pay shown here. Be careful with the head fixity. The round bar here, this shows that this is a pin support. Of course, this structure in itself, it can't start. Yeah, pin, it won't start. But consider this like a part of a bay, maybe a bigger structure, which have been extracted for our analysis. So you're saying this is a hinge support. It carries a rotating machine. Okay. This escorts a horizontal force at the girder level. The girder level is the beam level. Okay. This escorts a horizontal force at the girder level in form of 50,000 sine 11t. So the machine that is resting on top here escorts, or there is a forcing function out of that machine. And this forcing function, the force is in a sinusoidal manner. So it's harmonic. Then you are told to assume 4% critical damping. So there are two things that you have to calculate here. What is the steady state amplitude of the vibration? Steady state amplitude. So the forcing component comes into play. Again, you ask, what is the maximum dynamic stress in the column? Remember, the purpose of analysis, the analysis itself is not an end product. All the theory of structures units that you have studied and that you'll cover, I believe now you are left with about 7, if for those who choose it. All those analyses are not the end product. At the analysis stage, most of the time you end up giving the input for the design. Yeah? So in as much as we might be doing the analysis, and then once you get the moment and the reaction, we stop there. We know that these are input for a secondary step that you go to the design. And that's why for this question, I've introduced the second part, B, so that now we want down to C. It's like the design component, the design part. What is the maximum dynamic stress in the column? Now we want to take that column, we analyze it. Okay? We analyze that. And you are given what is the I, moment of inertia, what is the modulus, and what is Z. I'll leave Z for now. I want somebody to take there. What is Z? If you are given an exam Z, do you know what is it? Okay. And solution for part A, we are saying, what is the steady state response or amplitude? What is the steady state amplitude? So what we are required to obtain here is what is capital U. And the capital U, of course, from equation 68, we have capital U is UST over the root of that. Okay. And UST, of course, you knew UST is equal to F naught. You can go back here, you get UST is equal to F naught over K. The UST is static deflection. Now, so you look at that because you have the end. When you look at the question, of course, before you work it out, you look at what is required, what is given, what do I need to calculate? Z section modulus, good average, that's true. And at least you should know the section modulus for different sections, rectangular section, you know, and so on and so forth. So one, we have the K, because we know we are going to need K. K, the stiffness for the column. Remember, in I believe this should also be lesson 2, where we looked at the equivalent stiffnesses. So based on the fixity, end fixity, this is the thin rod. We have is 3EI over L. Okay. So, and because there are two columns, of course, it's summation, because it's like there's two springs in parallel. So it's just a summation. That's why I'm multiplying by 2. So you can punch your calculator there. I have not done that so that you can participate in the class. So you tell us what is the value there. Remember, L is given as 4. Okay. The natural frequency of the system, omega, is equal to K over M. K you have calculated. M is given here as 5,000 kgs. You obtain that. Now you are given ohm. This is the frequency of the forcing function, S. Can somebody be able to extract it from our statement, our problem here? Can somebody tell us what is ohm? And therefore, that ohm that you get, that is the frequency of the forcing function. Somebody can type that in the section, chat section. You're going to get R is equal to ohm over omega, which is equal to this just a ratio. Okay. Now, also the frequency, I mean, not the frequency, the damping ratio. Yeah. Xi, which is equal to C over C critical, is given in the AC equation. I hope somebody can be able again to pinpoint that. It's directly from this question. That's why I've left them blank so that you can see how easy it is to extract this information. And therefore, F naught, of course, F naught is equal to, yes? F naught. F naught. I'm waiting for somebody to give me these values. I'm waiting for somebody to tell me what is capital omega. What is the frequency of the forcing function from our question here? Can somebody pinpoint or extract or tell us what is the frequency of the forcing function? Okay. Alex Mogo, what is the frequency? Frequency of the forcing function. First of all, you have to identify which is the forcing function. Okay, and we know that once we know what is the forcing function, we know that we have F naught psi ohm T. Okay, so this is the F naught that we are looking for. This is the ohm that we are looking for. So Mutua Samuel, ohm is 11, and then you're asking a question. You should be sure. Ohm is 11. Once you identify this function where it is, you locate it. You just need to extract it. And as you can see, we are saying the rotating machine that is resting here, it's not shown here. The rotating machine should be somewhere here on top of this guard. The rotating machine, as a result of the rotating machine, there is a horizontal force at the girder level in form of, because of the rotating machine, in form of 50,000 sine 11 T. Okay, so it's obvious that this is the forcing function which emanates from this rotating machine. And now you can now write here, because I'm seeing, yeah, the answer is 11. You are correct. I was waiting for somebody else now to give us what is F naught. 50,000, yes. It's not F, it's F node. Okay. Oh, okay. You can even say call it F because maybe you are not using F for now. So this is 50,000. So this is F node sine ohm t. Ohm is equals to 11, and of course we expect it's 11. Right. Okay. Good. Gabriel Jr. Yes, true. 50,000 sine ohm 11t. That is the forcing function. So you can see you already have what is F node 50,000. You have calculated K. You have obtained R. Okay. And what is the xi is given? What is this xi? I don't know how you call it because in Greek it's xi. Okay. Somebody to tell us what is this is the damping ratio. What is the damping ratio from this equation? Okay. Jacqueline Mutua. Yeah, today we are solving together with you this problem because it's very, very easy. Okay. Jacqueline Mutua, are we together with us? But they tell people, I'm seeing now the number goes up, goes down. Why we are taking the attendance here is because we are tracking the time you log in and the time you get out. I have that data from my site. Okay. You know how long you stayed online on this class. Who else can help Jacqueline Mutua to tell us? Okay. How do you have assisted there? It's 4 over 100. I mean, it's 4%. Good. So what is difficult there? You see, we have already obtained quite easily the steady state amplitude. Steady state amplitude. Note here we are just concerned with the amplitude. If you ask what is the steady state response, steady state response. Now, steady state response is like it means you can be able to get the displacement at different times. All right. So for us to obtain that, it's just a matter of using this, bringing this part. Okay. The steady state response is the matter of bringing the sine part. This sine ohm t minus theta. You're asking for, I don't know whether it's this part, the steady state response, this part. But I believe you are going to see with an example later on. Now let's move to the second part. Now this second part, I have moved a step further. It's like of the design. So we are kind of not just using what we have learned here. It's like what we have learned here now, we move ahead and combine with what we learned in previous studies or in the previous lectures, be it in strength of materials, because that's where now you are analyzing about the section properties, and be it in theory of structures and in design. So we move, you say, so you want to calculate what is a maximum dynamic stress, like what is the stress in the column. Okay. So what you need to do, you have for the stress, there is this equation that is very useful. The equation of bending, you talk of E of R is equals to M of I is equals to F of Y. This equation is useful. Of course, in moment, sometimes F, this one, we sometimes talk of the delta like that. Okay. And then we can use this component because the relation that is standard and use this component. We want to calculate the stress, the F, and then this Y, of course, is descent from the neutral axis to the extreme fiber. This is the moment. This is a second moment of inertia. So if you don't have this Y, now that's why you're saying you need to know how to relate the section modulus. Okay, the section modulus is equals to I over Y, right? I hope you recall that. So you need to get the moment. And to get the moment, of course, our column, the load is applied, which you call the shear force, the shear load. Then you can get the like the shear force diagram. We'll be able to get the moment because the moment this is a cantilever, kind of a cantilever column, just need to take the shear force times this distance L, you're going to get the moment. So, and the shear force in the column cause the force F is equals to K times delta. And K, we have it. Remember, we are just taking, of course, even if we have another column here, okay, we are just talking of the load applied here. The deformation will occur on both columns. But the deformation is not a combination of this. It's not double combination that the way we can say combine the stiffness of the two columns. So the deflection is just one, the K is just one. And we have found what is the maximum dynamic, what is the maximum of the steady state response. Okay, so the steady state response, the forcing function produces a maximum displacement capital U. Okay, and this now to calculate the maximum shear force is done that you are multiplying by the stiffness of this column to get what's the shear force, and then you get what is the moment, and then you get what is the stress. Okay, so as you can see here, don't go back to this lecture trying to get where this equation comes from. This is now the combination of the knowledge. We say the knowledge is what remains after education, or what you started in throughout your formal education gets if it's forgotten. What remains? You look at the scenario, you recall, you start thinking of the approach or the kind of equation that can be employed. Be it whether you learned them in physics in high school, you learned it even in primary school science, but you look at the problem, the provided quantities, you start to analyze how well can I analyze this problem. Okay. Let me move a little bit faster because this second problem have got some component that provides or that brings in some new concepts, but the first part is quite easy. And for those people who have started looking at the tutorials, the one that I have provided for last year, you may find like some of these problems have already been solved there. You can look at them. So don't wait until the end of the semester. In fact, take the advantage of the starting when the time at this stage when the things are relaxed, so that you can do as much practice as possible with this. So a machine is weighing the 1750 kgs. So this machine, the weight of, now the machine is shown here. So the weight is given in terms of mass. So this is mounted on a simply supported steel beam as shown, and here you can see the roller support. This is the pin. No, it's hinged. I don't know. What is it? Yeah, it's hinged. A piston moves up and down in the machine. So there is some part component, a piston that's moving up and down. Remember, if there is no motion in this machine, it's just placed. It's just a dead dog. So there's no dynamic force. That's why we are bringing this concept of something is happening inside the machine, some rotary motion that brings about some dynamic load on the structure. And now, because of that, the machine, because of that piston that's moving up and down, the machine produces a harmonic force of magnitude at 175 and a frequency 60. So the machine produces this dynamic force at this frequency, right? So at this stage, even without going further, somebody can write the expression for the forcing function, okay? Barnabas Ball, you are writing that 50,000 F naught is equals to 50,000 sine 11t. No. Why no? It's because if you do like that, you'll be confused. If you look at our expression here, if you look at this expression, externally applied force, the force, the externally applied force, this is F naught sine omega t, sine om t. It's not F naught is equals to F naught sine om t. So if the way you have done the expression, you may end up having F naught, because now like the problem we have just solved, we found that F naught, and somebody indicated that, we found that F naught, yes, at time 901, William Wajau said F, and this is why I correctly said F naught is equal to 50,000. So if you use the expression you have stated, you'll find that your F naught is different, and your F naught is Y, while F naught is supposed to be a constant. Okay, so correct that. So I was saying, somebody should be able now here to write by just reading the second statement, the second sentence. Somebody should be able to write the expression for the forcing function. Now you are told, if you neglect the weight of the beam and you assume 10% of critical damping, now you have to determine one, the amplitude of the motion of the machine, the amplitude of the motion of the machine. So you have to calculate what? Amplitude of the motion of the machine, the amplitude of the forcing component, the U capital. And then you have to calculate what is the force transmitted to the beam support. So this is a new component, the second part too. And this is the part that I want us to dwell on, because the first part you can solve it quite easily. So I have provided the solution for the first part. Sorry for that. You can look at it. You are given the modulus, you are given I. So you can look at this quite easily. You are given, but I wanted you people to extract this even before. Oh, you already have that. I wanted you to extract this. Looking at this equation, I wanted somebody to give me what is the F naught, what is ohm, what is xi, and any other component that is given. But I have already done that for you here. You're given what is ohm, xi, F naught, EI. This EI I've already multiplied with that. You can calculate what is the stiffness. Okay, so I'm moving fast because it's like a repetition of what we have already done. Omega is given, R is like that. Amplitude is, of course, F naught, K like that. You substitute, you're going to get what is your answer there. I've moved very fast here because it's just a matter of substituting. Okay. I want us to look at forces transmitted to the foundation or to the support. Okay. Now, we are rephrasing, or no, we are rewriting again, not even rewriting, we are just copying and transferring it here for our reference, equation 53. This was the equation for damped case, of course, with forcing function. Now, for the damped oscillator, let me know, in that problem, if somebody is stuck somewhere solving part one, we can always go back to it, but I believe it's straightforward. Because I want us to have time to look at part two. Now, for a damped oscillator above, so this one we are calling an oscillator. It's moving to and fro, so it's an oscillation. So a dynamic system, we are calling it an oscillator. So for a damped oscillator above, the force transmitted to the support, remember the support is here on this, where they are fixed, where the spring and the dashboard are fixed. This is now where we are saying this is the support. So the force that is transmitted to the support will be transmitted through one, the spring and the damper. So the force that will be experienced on this support is transmitted. The F total transmitted to the support is transmitted by the stiffness, by the column, by the spring stiffness, K, and the damping, CV. Now, the steady state solution to the above motion is given by equation 64. Okay, the steady state response for the motion here, of course, was given by equation 64. We are referring. And we have seen the forcing, the force Ft that will be transmitted to the foundation is Ku plus Cv, or Cu upper dot. Now, of course, remember how we used the polar coordinate to condense our equation, and we came up with what was theta, and U, this one now is where we are able to get the the amplitude of the steady state response in a simplified manner when you use the ratios. So all these equations are repeated. So if you differentiate equation 64, we are looking at equation 64. This is the solution of the steady state response. We are saying if you differentiate equation 64 and substitute in equation 71, now this is where now we have the force transmitted to the foundation, because we want to substitute. We have already U. We want to substitute U, the solution, this 64, and to get now the velocity, you differentiate once. So you differentiate and substitute in equation 71. So all these equations 71 up to 76 is just a matter of differentiating and substituting U, and then simplifying using the ratios that we already have defined previously, and introducing just a new angle phi, okay, which is given by theta minus beta. Okay, don't be surprised or worried about these angles. Because that's the definition of the phase angles. Therefore, you are going to get tan theta equals to as shown in this equation. Okay, and from equation 68, 68 is where now we have the displacement or the amplitude of the steady state response, U capital U. From that equation, the maximum force transmitted to the foundation, to the support or to the foundation. So from equation 68 and 73, we are going to get Ft to be equals to F naught, all that. And we define a ratio, we call it transmissibility, as the amplitude of the force transmitted to the support and the amplitude of the applied force. So transmissibility ratio, TR, is equals to Ft over F naught, is equals to the square root of that. Now, using equation 71 to 78, you can be able to solve part 2 of our example 6. And this is so in this tutorial. We agreed that I provide the enhanced tutorial with minimal explanation. So you just need to go to this tutorial. It was tutorial number 2 for last year. You can be able to see the solution for the second part. But actually what you just need to use is that this is the Ft, the force transmitted to a foundation Ft. You just need to get what is F naught. What is Xi? Xi is already given. What is R, which is ohm over omega? Only those components. Yeah, you're saying we need to get what is Xi, what is R, what is F naught, and we use the equation 77. So as you can see, we already, from this equation, from this problem, we already know what is ohm. What's that? Actually, we know what is R here. We already calculated that. And we know what is F naught is given. And we know what is Xi, damping ratio, 0.1. So it's as easy as it can be seen here. Yes, the derivation was task 2, but again, the application of equation 77 is quite easy. So the solution to this, you can look at this tutorial. And at the same time, you can look at the problem in our main reference, that is by Mario Paz. So remember, for those people who may not be remembering the references, I always put, if you go to the description part in this video below there, you're going to see the reference book that we are using. And the first one is the main reference. And I remember for this class, I shared that link because, as I said, during the time of COVID, we had the access of that book. So I don't think you can get it free online, genuinely. But during that time, we are given the link to obtain that book. Okay? And that is as easy as it can be seen. Okay? And I would like to stop there so that I can take any question that might be there. Any question that you might be having, you can be able to respond that. I'm looking at the chat section to see whether there's any question that have been dropped there. I believe most of them that you have mentioned, I've already clarified them. So look at those examples. Let me know if there's any part that may need clarification. Because for today, I would like to stop there so that next time we are going to look at when the forcing function is not harmonic. It's a general, non-periodic wave. Okay. So any question? The floor now is open to question. If not, then I like to call it a day. And thank you for the attendance, of course. Make sure, if you're a member of this class, just make sure that you leave your registration number. Okay, that's it for today. Any question later on, as you do your revision in any of the videos, you can always leave it in the comment section and then we address it together. I can address in the comments. And as always, I say always like the videos, like share, comment, leave your comment there, share with your friends, tell them to subscribe. Even those outside this university, we want to reach as many people as possible as we share knowledge. After next week's lecture, we are going to, next week is the end of the free vibration, of the single degree of freedom systems. So I believe after next week's lecture, we are going to have our first CAT, which should cover the free vibration, the single degree of freedom cases. Okay, thank you. That's it for today. Allow me to end this broadcast.
Okay, before I leave completely, there are questions maybe you are hearing me answering. So we usually have a WhatsApp channel. So there are people, mostly those who are not part of this class, who like asking through the channel. I'm going to share the link so that you can follow that channel, the WhatsApp, so that you can also be utilizing and benefiting from it. So otherwise, continue practicing, continue preparing. Next week, maybe we have 1 week or so, then we have our CAT. That's all for today. You can see no more question here in this chat, so bye-bye.